spiffy. Only sibling is the city. This playground is the lobby. Has a palette.
In this last video, we're going to talk about the Galois group of Q adjoins zeta n over Q in terms of a prime factorization of n. So let's suppose that n factors into this product p1 to the a1 times pk to the ak, where each one of these exponents is a positive integer and the pi are distinct primes. So we can see that if you take a primitive nth root of unity, zeta n, and you raise it to the p2 to the a2 times p3 to the a3 times pk to the ak power, what you get is an element in the group of nth roots of unity of order p1 to the a1. What you get is a primitive p1 to the a1 root of unity. So that shows that if you take q adjoin zeta p1 to the a1, that's a subfield of q adjoin zeta n. So you have these sort of prime power cyclotomic subfields inside q adjoin zeta n. So there's nothing special about one here. Q adjoin zeta pi to the ai is a subfield of q adjoin zeta n for each I. And now we can apply results from earlier that we have about composites and intersections of cyclotomic fields. So by the result from earlier, the composite of all of these q adjoin zeta pi to the ai extensions is q adjoin zeta n. Where, okay, really maybe what I should say is the composite of q adjoin zeta p1 to the a1 and q adjoin zeta p2 to the a2 is q adjoin zeta p1 to the a1 times p2 to the a2. We proved this for two extensions, but then you could just go from 2 to 3. You apply this result several times to apply this to k, the composite of these k fields instead of just two of them. So I'll leave the details to you to think about a little bit. What about intersections? Well, because the GCD of p1 to the a1 and p2 to the a2 is 1, we see that the intersection of q adjoin zeta p1 to the a1 and q adjoin zeta p2 to the a2 is q. So if you take the intersection of any two of these q adjoin zeta pi to the ai's, what you get, any two of those intersect just in q. So now we can apply this result from the last lecture about the Galois group of the composite of extensions where the intersection of the two Galois extensions you're taking is just the original base field f. This corollary 22 from section 14.4 now shows that the Galois group of q adjoins zeta n over q is the direct product of the Galois groups of these prime power pieces. So what is that saying? The Galois group of q adjoins zeta n over q is isomorphic to the Galois group of q adjoins zeta p1 to the a1 over q cross Galois group of q adjoins zeta pk to the ak over q. And in some sense, we already knew this because we know that this one is isomorphic to z mod n z star. This is isomorphic to z mod p1 to the a1 z star cross. So under that isomorphism between the Galois group of q adjoins zeta n over q being isomorphic to z mod n z star, what we get is exactly the statement of the Chinese remainder theorem, that z mod n z star is isomorphic to z mod p1 to the a1 z star cross z mod pk to the akz star. Okay, so this part we know. And the statement about the identification with the Chinese remainder theorem, I'll leave as an exercise. This is exercise 13 in section 14.5. Okay, so we understand what Galois groups of cyclotomic extensions look like. I'll pause and erase and give a definition and talk about some related questions. I want to end this lecture by talking about some things that are beyond the scope of this course, but that you might want to keep in mind for the future. So first, a definition. An extension k of f is called an abelian extension if k is a Galois extension of f and the Galois group of k over f is abelian. So one example that we know is that cyclotomic extensions are abelian. So q adjoins zeta n is an abelian extension of q for any n. Also, subfields of abelian extensions are abelian. This is using the fact that every subgroup of an abelian group is automatically normal. Okay, so there's a really neat application at the end of section 14.5 of Dummett and Foote, where you can show that for any finite abelian group G, there exists a Galois extension K of Q with the Galois group of K over Q isomorphic to G. Okay, so this uses a lot of the material that we've developed in this section, but it also uses something about the existence of primes that are congruent to 1 mod n for different n. So I encourage you to check this out and read through this application, but this is not something you need to know for exams for this course. But this brings up an interesting question, which is, if I hand you a group, can you find a finite extension of Q that is Galois, that has that particular group as its Galois group? So this is the subject of the inverse Galois problem, which is an active area of current research. So let's say that G is a finite group. Does there exist a Galois extension, K of Q, with the Galois group of K over Q isomorphic to G? So what is this application saying? It's saying if G is a finite abelian group, the answer is yes. So this is a solution to the inverse Galois problem for finite abelian groups over Q. You could ask this same question, inverse Galois problem, saying you have a finite group. You want to know if there's a Galois extension K of some other field, not necessarily Q, maybe like Q adjoin I, or maybe something completely different. So does there exist a Galois extension of K over F with the Galois group of K over F isomorphic to G? And there's a lot that we don't know about this problem. Okay, so what do we know about abelian extensions? Cyclotomic extensions are abelian, abelian extensions of Q. Subfields of cyclotomic extensions give abelian extensions of Q. Are there any others? And the Kronecker-Weber theorem says that every abelian extension of Q is contained in a cyclotomic extension of Q. Okay, this theorem is hard to prove. It's something that I actually talked about quite a bit when I taught the Math 232 graduate sequence, the graduate number theory sequence. This is sort of one key result in the beginning of a subject that's known as class field theory. So this is a really interesting point of contact between the Galois theory material that we've been talking about here and then algebraic number theory also. Okay, so let me just point out that here, this Q is very important. We understand now where abelian extensions of Q come from. They come from cyclotomic extensions and their subfields. But what about abelian extensions of other fields? Like, what about abelian extensions of a field like Q adjoin I, or some other more complicated field as your base field? And this leads to some really interesting questions in algebra, number theory, and is also a topic of active research interest.